All right, today we're going to dive into one of the biggest ideas in the history of science, Einstein's special theory of relativity. And trust me, this wasn't just some small update to the physics rulebook. It completely shattered everything we thought we knew about space, time, and, well, the universe itself.
To really get how huge this was, you have to understand who Einstein was up against. I mean, he was challenging the undisputed heavyweight champion of physics for over 200 years, Sir Isaac Newton. This wasn't just a friendly debate. This was a complete revolution, a total takedown of the old way of thinking.
So you might be asking, why was this revolution even necessary? Wasn't physics doing just fine? Well, not exactly. By the end of the 1800s, physics was secretly in big trouble. That perfect, predictable, clockwork universe that Newton had described was starting to show some really deep cracks.
You could think of it like a detective story, where the detectives were completely stuck. They had three major roadblocks. First, there was this conceptual problem about a mysterious, invisible substance called the ether that was supposed to fill all of space, but nobody could find it. Then there was an experimental problem. A huge experiment was built to detect this ether, and it failed spectacularly. But the biggest problem of all was with the theories themselves.
And this was the real showstopper. The two fundamental pillars of physics were basically at war. You had Newton's laws, which were perfect for describing how things like planets and cannonballs move, and then you had Maxwell's equations, which were brilliant for describing light. The only problem, their rules completely contradicted each other. Physics had broken itself.
So what was the problem? It all came down to an idea that Newton himself had, which you can see in his famous bucket experiment. He thought of the universe as having a fixed absolute stage, an absolute space that never moved. And he believed time was absolute too, like a giant cosmic clock that ticked at the same rate for everyone, everywhere. It sounds like common sense, right? Well, that piece of common sense was about to get completely demolished.
And into this complete mess steps a young patent clerk named Albert Einstein. In 1905, he proposed a solution. And it wasn't based on some ridiculously complicated math, but on two stunningly simple rules that would, quite literally, change everything.
Okay, so his first rule is basically like a declaration of democracy for physics. It just says there's no special, correct point of view in the universe. Whether you're standing on the ground or cruising in a train at a steady speed, the laws of physics are exactly the same for you. There's no such thing as being truly at rest.
Now, rule number 2. This is where reality starts to get really weird. Einstein said that the speed of light is the universe's ultimate speed limit. But here's the part that breaks your brain. He said everyone measures it to be the exact same speed, no matter what. I mean, think about it. If you drive towards an oncoming car, its speed relative to you is faster. That's common sense. But not with light. It doesn't matter if you're flying towards a light beam or away from it, you will always clock its speed at the same number. Always.
And here's the kicker. That's it. Those two simple ideas were all it took. Suddenly, the ether wasn't needed anymore. The big fight between Newton and Maxwell was over. But in solving those problems, Einstein's rules unleashed a whole set of consequences that just turned our intuitions about reality completely upside down.
And this is where we get the payoff. So what happens when you take these two rules and just follow them to their logical conclusion? Well, you step into a very strange new world where time itself is no longer fixed. It becomes flexible. The very first casualty of special relativity is an idea we all take for granted. The idea of a universal now. The notion that something is happening right now on the other side of the galaxy is, according to Einstein, completely meaningless. Let me try to explain. Imagine a really long spaceship flies past you, and two balloons pop at the exact same moment, one at the front and one at the back. To you, standing still, you'd see them pop at the same time, simultaneous. But think about the pilot. She's moving towards the light from the front balloon, so that light reaches her first. To her, the front balloon popped before the back one. So who's right? Here's the crazy part. You both are. Whether events happen at the same time depends on who's looking.
So, if we can't even agree on what now is, what does that mean for the flow of time itself? Well, this leads us to the most famous, most sci-fi consequence of them all, time dilation.
To get this, let's use one of Einstein's favorite tools, a thought experiment. Imagine we have a light clock. A tick is just the time it takes for a little pulse of light to bounce from the floor to a mirror on the ceiling and back again. Now, if you're inside the clock, watching it, the path is simple, right? It just goes straight up and straight down. But now, let's say you're standing on the ground.
watching this light clock fly by on a train. From your perspective, that light pulse doesn't just go up and down. Because the clock is moving forward, the light has to travel on a longer diagonal path to catch up to the mirror, and then another diagonal path to get back to the bottom. It travels in a V shape.
Okay, so let's bring back those two unbreakable rules. Rule number 2, the speed of light has to be the same for both the person on the train and for you watching from the ground. But, as we just saw, from your point of view, the light traveled a longer path.
And that leaves you with only one possible conclusion. And it's a wild one. If something travels a longer distance, but at the exact same speed, it must take more time to make the trip. Which means you, on the ground, literally measure the tick of that moving clock as taking longer than a tick of your own clock.
This leads us to one of the most famous phrases in all of physics, shown here in French from one of the sources, les horloges en mouvement retardent. It means, simply, moving clocks run slow. From your point of view as a stationary observer, time itself is actually passing more slowly for anything that's in motion.
Now, you don't notice this driving your car because the effect at everyday speeds is absolutely tiny. But just look at this graph. As you get faster and faster, closer to the speed of light, this time-slowing effect just shoots upward. It goes almost vertical. For something traveling near the speed of light, time would slow down to a crawl.
So what does this all mean? If time is relative, if now is relative, what is the true nature of reality? Well, Einstein gave us a completely new picture to look at.
See, Newton's universe was like a rigid box. You had absolute space and absolute time just ticking away. Einstein's revolution was realizing that space and time are not separate things at all. They are woven together, part of a single, four-dimensional fabric that he called space-time.
This diagram is great because it shows you where special relativity fits in. It's the theory that governs reality at very high speeds, so long as you don't have super strong gravity. It's the essential bridge between the classical physics of our everyday world and Einstein's next big idea, general relativity, which finally brought gravity into this weird new picture.
So really, the most important thing to take away from all this is that your reality is personal. Your ruler and your clock are not absolute. The way you experience time and space is unique to you, and it all depends on how you're moving through the universe.
And this really leaves us with a final, pretty mind-blowing thought. Einstein showed that time, which feels like the most constant and relentless thing in our lives, is actually flexible. So it just has to make you wonder, if time can bend, what other fundamental parts of our reality are just waiting to be seen from a completely new perspective?